Have you ever watched a roller coaster climb slowly to the top of a hill, only to rush down moments later at incredible speed? That dramatic switch from slow motion to high speed is a perfect real-world example of mechanical energy in action. Mechanical energy is the energy a body possesses because of its position or motion. Think of it as the total energy that a body has because it's either moving or held at some height, or both. This mechanical energy can exist in two major forms. One is potential energy, and the other is kinetic energy. In real-world systems, both often act together. So the total mechanical energy is nothing but the sum of a body's kinetic energy and its potential energy. Mechanical energy exists in two primary forms: potential energy and kinetic energy. Potential energy is the energy stored in a body due to its position or configuration, while kinetic energy is the energy a body possesses due to its motion. For example, a body placed at a height or a compressed spring stores potential energy. These systems have the ability to do work when their position changes or when the spring is released. On the other hand, a moving bullet or a speeding car possesses kinetic energy, the energy of motion. Interestingly, mechanical energy can shift between these two forms. Depending on the physical state or movement of the object, potential energy can transform into kinetic energy, and vice versa. Take a falling object, for instance. As it descends from a height, the potential energy it held is gradually converted into kinetic energy. This interplay is a fundamental concept in physics and helps us understand many natural and mechanical processes. Potential energy is the energy that a body possesses simply because of its position or configuration. This stored energy has the potential to do work when the position of the object changes. For instance, if we consider an object of mass n placed at a height h above the ground, the potential energy it stores is given by the formula Pe equals m multiplied by g multiplied by h, where g is the acceleration due to gravity. This means that the higher the object is placed, or the more massive it is, the greater its potential energy. In simple terms, both mass and height play a role in determining how much energy is stored. A real-world example of this is water stored in a dam. Because the water is held at a height, it has high potential energy. And this stored energy doesn't just sit there. It can be harnessed to generate electricity by letting the water flow down through turbines. This is how many hydroelectric power plants operate. Kinetic energy is the energy that a body possesses because of its motion. Unlike potential energy, which depends on position, kinetic energy depends on how fast the object is moving. The formula for kinetic energy is kinetic energy equals 1/2 multiplied by mass multiplied by velocity squared. That is, Ke equals 1/2 times m times v squared. This tells us that the faster an object moves, the greater its kinetic energy. In fact, since velocity is squared in the formula, even a small increase in speed results in a much larger increase in kinetic energy. Consider examples like a moving ball, a running train, or even a falling raindrop. All of these possess kinetic energy due to their motion. And here's something important. Kinetic energy is always a positive value. That's because velocity squared is always positive, no matter the direction of motion. So, kinetic energy directly depends on the square of the speed of the object. Mechanical energy is the sum of two components, potential energy and kinetic energy. So the total mechanical energy of a system is given by the expression mechanical energy equals potential energy plus kinetic energy. According to the law of conservation of mechanical energy, the total mechanical energy of a system remains constant, provided there are no external forces acting on it, like friction or air resistance. Let's take the example of a freely falling body. As it falls, it loses potential energy, but at the same time, it gains kinetic energy. The key idea is that the loss in one form is exactly balanced by the gain in the other, so the total remains unchanged. Throughout the fall, although the individual values of potential and kinetic energy change, their sum stays constant. This principle is not just theoretical, it's practically applied in designing roller coasters, pendulums, and even satellite motion, where energy conservation ensures predictable movement and efficiency. Mechanical energy isn't just a textbook concept, it's all around us in action. In hydroelectric power plants, for instance, water stored at a height has potential energy. When released, this energy drives turbines and generates electricity. In vehicles, it's kinetic energy that keeps them moving. This energy comes from the combustion of fuel, propelling the car forward. Consider a bow and arrow. When the string is pulled back, potential energy is stored. The moment it's released, that potential energy is converted into kinetic energy, launching the arrow forward. Most machines we use, from washing machines to engines, operate using a combination of both kinetic and potential energy, allowing them to perform work efficiently. In fact, mechanical energy is fundamental to everything from simple hand tools to advanced engineering systems, making it a key driver of motion and innovation in the real world. Let's quickly revise what we've learned about mechanical energy. Mechanical energy is the energy possessed by a body due to its position or motion. It has two forms, potential energy and kinetic energy. Potential energy is stored energy due to position and is given by the formula PE equals m into g into h. Kinetic energy is energy of motion and is given by Ke equals 1 divided by 2 into m into v squared. The total mechanical energy of a body is the sum of its kinetic and potential energies. I hope now you understand how motion and position together give rise to the beautiful interplay of energy around us. See you in the next topic.